Welcome to the Unit 9 Section 2 video on key features of exponentials from a graph.
Recall that an exponential function is a function of the form f of x equals ab to the x, where a cannot be 0, b cannot be 1, and b is greater than 0. Just as we could identify certain key features of linear and quadratic functions, we can also identify similar key features for exponential functions. So let's talk about those key features. The first is the x-intercept. As always, it is the point where the graph crosses the x-axis. Same for our y-intercept. It is where the graph crosses the y-axis. Our domain is the set of all x values, and for exponential functions, your domain will always be negative infinity to positive infinity. Our range is the set of all y values, and our range is either going to go to positive infinity or negative infinity from some value. Our positive interval is going to be the set of x values with positive y values, where the graph is above the x-axis, and the negative interval is still where the graph is below the x-axis. Increasing interval is still where we're increasing from left to right, and decreasing is where we're decreasing from left to right. So an exponential function will either increase everywhere from negative infinity to positive infinity, or decrease everywhere. If it's increasing everywhere, then you have no decreasing interval. If it's decreasing everywhere, then you have no increasing interval. And then finally, a unique feature to exponential functions is the horizontal asymptote. It is the horizontal line that the graph approaches as x approaches either positive or negative infinity. So looking at this graph, as x approaches negative infinity, so we're looking at the left-hand side, we are approaching that horizontal asymptote line, which is indicated by the dashed line. Let's talk a little bit more about end behavior. Recall that end behavior describes the behavior of the graph of the function at the ends of the x-axis. For exponential functions, f of x approaches positive infinity or negative infinity on one end, and f of x approaches the horizontal asymptote on the other end. So for an exponential function, like this one, where we're exhibiting exponential growth, we have our asymptote below the graph, and as x approaches infinity on the right-hand side, we're looking at the right-hand side of the graph, f of x is approaching positive infinity because our graph is pointed upward. Now, if we take a look at the same graph and look at the other side, and look at the left-hand side where x is approaching negative infinity, you'll notice that f of x is approaching negative 4. That horizontal asymptote is a line that the graph is never going to touch. Your exponential curve is getting closer and closer to that horizontal asymptote the farther into the negative numbers we go, but it's never going to touch that horizontal asymptote. No matter where you are, you can zoom in and still see space between your graph and the asymptote. So negative 4 will never get touched by this graph. We'll get infinitely close to it, but we will never get there. So let's do a few examples of identifying some key features. Starting with the x-intercept. Well, here, since we are approaching the x-axis, we have no x-intercept. Our y-intercept is at 0, 1. Our domain is negative infinity to positive infinity. Remember, that will be your domain for all exponential functions because you will have an arrow on the left and an arrow on the right. Our range, however, is not going to be all real numbers. Because we are approaching the x-axis but not going below it, our range will be from 0 to infinity. Our positive interval, since we're always going to be above the x-axis, will be negative infinity to positive infinity, leaving us with no negative interval. And this graph from left to right is always decreasing, so we have no increasing interval and a decreasing interval from negative infinity to positive infinity. Our horizontal asymptote is the x-axis, that's what we're approaching, so that's at y equals 0. And our end behavior, as x approaches infinity, f of x is approaching the asymptote, which is 0. As x approaches negative infinity, f of x is pointed upward, so we are approaching infinity. In example 2, our x-intercept here is at 1, 0. Our y-intercept is at 0, 4. Our domain is from negative infinity to positive infinity. Our range goes from negative infinity to 8. 8 is where the line levels out, and we're approaching an asymptote. Our positive interval goes from negative infinity to 1, and our negative interval goes from 1 to infinity. Our increasing interval is none because it is decreasing the whole time. So we have negative infinity to positive infinity for our decreasing interval. Our horizontal asymptote, we are approaching y equals 8. And our end behavior, as x goes to infinity, f of x goes to negative infinity because we're pointed downward. As x goes to negative infinity, f of x approaches the asymptote, which is 8. For example 3, we have no x-intercept because our asymptote is below the x-axis, so no x-intercept, but we do have a y-intercept at 0, negative 4. Our domain is all real numbers. Our range goes from negative infinity to negative 3. Our positive interval, well, since the graph approaches an asymptote below the x-axis and it is going downward from there, we are never going to go above the x-axis, so we have no positive interval. So that means the entire graph will be negative. We're increasing from left to right, so we have all reals for our increasing interval with no decreasing interval. Our horizontal asymptote is at y equals negative 3, and as we take a look at our end behavior, as x approaches infinity, f of x approaches our asymptote, which is negative 3, and on the other end, as x approaches negative infinity, f of x is pointed downward, also approaching negative infinity. Recall for an exponential function of the form f of x equals ab to the x, exponential growth occurs when b is greater than 1, and exponential decay occurs when b is between 0 and 1. We can compare the similarities and differences of key features for growth and decay. So we're going to do that here in this table. So our domain for our exponential growth function 2 to the x is negative infinity to positive infinity, but so is our domain for 1/2 to the x, which is our decay function. So you'll notice domain always going to be negative infinity to positive infinity, whether you have growth or decay. Our range, comparing these two functions where the only thing we change is growth or decay, our range is 0 to infinity for both. So changing from a growth function to a decay function, where that's the only change you make, does not impact your range. Your range will stay the same for either. Your x-intercept also going to be the same. In this case, it's none. Your y-intercept is also going to be the same. In this case, 0, 1. Your horizontal asymptote also stays the same. It is 0. And your end behavior is going to be one thing that changes, but you're still going to have the same elements. Your end behavior for growth, you're going to infinity on the right side, but you're going to your asymptote on the left. For decay, it flips. You're going to your asymptote on the right, and you're going to infinity on the left. So just a little bit of comparisons between growth and decay. Changing from a growth function to a decay function, but changing nothing else, does not change many of our key features. Recall, the average rate of change is a ratio that compares the amount of change along the y-axis and the amount of change along the x-axis between 2 points on the function. So, more commonly, in math terms, we've said that it's y2 minus y1 over x2 minus x1. You've seen this a couple of times now. That was our slope formula when we did linear functions, and we did average rate of change when we did quadratics. Average rate of change for exponentials works exactly the same way. You want 2 points, and you want to see what your change is between those 2 points. So this formula is used whether the average rate of change is determined using an equation, graph, or a table. So let's start with an equation. You're going to substitute the first x value into the equation, solve to get y. This will be your first point. Substitute the second x value into the equation, solve to get y, this is your second point, and then plug both points into the average rate of change formula and simplify. So let's do a couple of examples, starting with A. We are given the interval 2 to 4. Those are our x values. So you're going to plug those x values into your x, and you're going to get your y values that go with it. Okay, so we do 2 squared, which is 4, and 2 to the 4th, which is 16. Then we plug in our 2 points, which we got, into our average rate of change formula, and we simplify to get 6 as our average rate of change between those two x values given the equation 2 to the x. For B, we have an exponential decay function, but we're going to do the exact same thing. We're going to take our -1 and plug it in, find our y. We're going to plug in our 1 and find our y. That gives us our 2 points, and we can plug that into our average rate of change formula, plugging in our x1 and our x2 and our y1 and our y2, and we can simplify to get -3/2. To do average rate of change from a table, you're going to find the first x value in the table and the corresponding y value. This is your first point. Find the second x value and corresponding y value for your second point, and then plug both points into your average rate of change formula and simplify. So let's do this with a table. So we are given the interval 0 to 2. So we have 0, 4, and 2, 16, which we pull directly from the table. And then we just plug it into our average rate of change formula to get 6. Same thing for B. We go from -2 to -1, pull the 2 points from the table, plug those points into your average rate of change formula, and then simplify to get -24. For average rate of change from a graph, you're going to find the first x value on the x-axis, follow the vertical line until you meet the graph. This will be your first point. Do the same for your second x value to find your second point, and then plug your points into the average rate of change formula and simplify. So let's find the average rate of change over the given interval for these graphs. So from -4 to -2, you are going to find -4 on the x-axis, follow that down to your graph, and you're going to find that the y value that goes with it is -5. For -2, you follow that down, and you find the y that goes with it is -2, and then plug it into your average rate of change formula, and you get your final answer of 3/2. For B, we're going to go from 1 to 3. So we follow 1 down to the graph, and we find -3. We follow 3 over, and we're crossing the x-axis, so that's actually our x-intercept. So 3, 0 is our second point. And we plug those values in to get 3/2 for this one as well.
Thanks for checking out my video in the Foundations in Algebra series. You can subscribe to my channel. I've got the next video queued up for you, and if you need to check out any of the videos in the course, I've got the course playlist for you here as well. Thanks for watching.